А где, собственно, мел? Обычный белый, да. Никакой другим им мне не нужен. Да. Никаких других я, в принципе, не использую. Это тоже белый. Замечательно.
Какой год? Это было 80. Hey guys, before we resume, there is one announcement that tomorrow the schedule is different. The coffee will be served at 9. And then the talks will be from 9:30 to 1, so that the participants can leave earlier.
Talks start at 9 and begin at 9:30. Что это значит?
Right.
Как это понять? So talks from... Вера, у меня исторический вопрос. Ты с Сашей познакомился на семинаре Гинфонда или как-то еще? Я хочу узнать, я тот человек... Значит, раньше меня.
Yeah, let's.
Я хотел сказать, что я знаю Сашу больше всех.
Yes, so let's start the afternoon session. Let's continue the afternoon session. So our last speaker today is Victor Ginzburg, who will tell us about Chern classes of quantizable sheaves and characteristic cycles.
Thank you very much for the invitation. In fact, it seems like I'm the person who knows Sasha longer than everyone except Vera Serganova. I checked it, and it seems. And also, I met Sasha at the Gelfand seminar, and then since then we discussed many things, mathematical and non-mathematical, and in various ways, many aspects of our life in the Soviet Union was quite similar. Just to give an example, both of us liked not to get up too early. And at some point, I learned that there was a kind of unwritten rule that one shouldn't call Ginzburg before 11 a.m. and Goncharov before 1 p.m. Is that time correct? 12. Okay, before me. Somehow I believe the difference was 2 hours, not 1 hour. Okay, so now let's. No, he respected this. He respected it. Well, because he didn't tell him not to call. There were other things. The list is not just one item, but let me stop here and go to math. So this is a joint work with Vladimir Baranovsky, and it was motivated by a question by Roman Bezrukovnikov and Ivan Losif some almost 10 years ago, I believe. And they solved the question they wanted in the case of quiverite, the setting they used it. And finally, we were able to solve it in general. All right, so let me fix the notation. So X is a smooth quasi-projective symplectic variety. Of dimension, everything is over C. So of dimension 2n, so everything is over C. Thanks. Okay. And so, right, so we are interested in what's called the formal deformation quantization of the structure sheaf of X, and I'll denote this as O of H bar. So this is formal deformation. There may be many, maybe none, but I assume that there is one. So in other words, it's a sheaf of flat C of double bracket H bar algebras such that reduction mod H bar is the structure sheaf. All right. What else?
But it's supposed to be flat only on some final set, or
I think just flat, or is there any
flat?
flat means flat? Yeah, I think as a sheaf. So, I mean, you can
So it's
receive.
a flat sheaf of algebra.
Yeah,
Sheaf of
flat.
algebra.
I don't know what it does. One has to say sheaf of flat algebras or flat.
Global sections, do they have to be flat in H bar?
No.
So that's no.
Okay, so also let me fix the following additional data. So I fix y in X, a closed, possibly very nasty, like singular reducible subvariety. And typically it will be nasty. Not possibly, possibly, what is it called? With many components. Singular. And I also fix a coherent sheaf. On X, such that it is supported on Y. Supported on Y. And for technical just reasons, I would require that the support may be smaller than Y itself, but it should have the same dimension as Y. So some irreducible components of the support have to be irreducible components of Y, but there may be something else. So such that. In principle, I could take Y to be the support, but technically it's more convenient to do this. So in this situation, one has a Chern character map with support. So it assigns to my F, and so I'll denote it by CH sub Y of F. So this is a non-homogeneous cohomology class, so it looks like CH over I Y of F, where CH over I sub Y of F sits in the cohomology with support 2I sub Y of X, and this is the rank cohomology with support. So in particular, I could have replaced C by any field of characteristic 0 if nothing changes. All right, so cohomology with support has some basic properties. So first of all, it is, I mean, all of them are completely standard. So,
So you want Y to be fewer dimension?
No. No, I mean just dimension Y means dimension of the maximal dimension of irreducible components. There may be something smaller, but I don't care. So everything works. All right, so now there are basically two properties and I will use. So first of all, cohomology with support vanish in certain degrees automatically. Namely, this is 0 for all I very small. So namely, I is less than the codimension of y in X. So they cannot be too small. And the critical one has a simple interpretation. Namely, if I take CH of degree equal to the codimension of y, the y of f, then it has the following interpretation. If I cap it with a fundamental class of X, so use Poincare duality, then I go to homology, and this homology class is equal to what's called support cycle of F. And I'll denote it by sup in the square brackets, which is by definition formal linear combination of some multiplicities m sub alpha of F times the fundamental classes y like this, where the y's, y alpha, the y alphas are the irreducible components of y of maximal dimension. So I don't count.
But does it matter that you have components of smaller dimensions?
No, because the codimension will be even bigger and yeah, so it doesn't matter. Yeah. They may be, but it doesn't affect. All the statements are still correct. So where y sub alpha are the irreducible. So in applications, actually, they will never be smaller, but essentially the irreducible components of y such that dim alpha is equal to dim y. All right, so this is probably everything. So now we go back to our quantum story. And so given this f, I need to, sorry? Yeah, it's movable, yeah. So a quantization of f is a, well, it's what you expect it to be, is a coherent OH bar module, which is flat over the formal power series. So it's a sheaf. So first of all, I need a notation for it. All right, it's now but there may be many quantizations, but I will use this notation for, which is flat over C double brackets H bar. Well, such that this reduction mod H is mod H bar is F. In this setting, there is a notion of coherence, which one defines in the usual way some surjective, I mean, some co-kernel of some map between. Ask Vanya, he is an expert in this.
It's a module of type of algebra, so
yeah. I think the notion of coherence works in some ring spaces or some sort of very general setting. So globally, it's just finitely generated. That's all. And in fact, these algebras are all Noetherian, so global sections are all Noetherian. So there's absolutely no issue here. Okay, and now the first key result, a famous theorem of Gaber, says that if f has a quantization, then every irreducible component of its support has dimension at least 1/2. It is coisotropic subvariety, but I don't care. I just use dimension. This is my answer. All right. So now here is our first theorem. So first, the most interesting case is the case where the dimension is exactly 1/2, which is called holonomic. And so our theorem is, so in fact, it can be generalized to some statement without this assumption, but then in this, I just ignore it because this is the only case I care. So theorem 1. So if the dimension under my assumptions, we have this y which has the same dimension as x as the support. So if the dimension of y is n and f has at least one quantization, then the Chern character sits in a single degree, in the critical degree. So it's precisely this thing. So the Poincare dual of this Chern character is precisely the support cycle. So this can be generalized for some. So if y does not have this dimension but has a high dimension, then the Chern character vanishes in a certain range of degrees. It's not a single degree, but one can explicitly write what the degrees are, but I don't care. All right, so now to formulate the second theorem, let's introduce the following notation. So we have to go to Laurent series. So this is this. And now I'm looking at the global sections. So A is supposed to be K tensor. So I extend scalars from formal power series to formal Laurent series. So this is an associative, not necessarily commutative. K algebra, where K is this Laurent series. And therefore, if I take the global, the cohomology of my quantized sheaf, H bar, and extend scalars again, then this is a module over this algebra A. Sorry. Yeah, I didn't finish. Is that, sorry, yes. Yeah, continue, please. Yes. All right. And now one last comment that if y is compact, in other words, a projective variety, then all these cohomologies are finite dimensional over K. Well, it's kind of, we're taking global sections of cohomology over a compact set, so it's finitely generated. All right, so this is what I have. So now I'm ready to formulate, I guess, the second theorem. Right. Okay, so theorem 2. So now we assume that the dimension of M is critical. So we're in the holonomic case, and also Y is compact. And also suppose we are given a collection. Let's F alpha be a collection of coherent sheaves. With support in Y. And suppose I'm given a quantization for each of those. And F alpha bar, F alpha sub H bar, a quantization of F alpha such that we have the following conditions. So first of all, they do not have cohomology except in degree 0. So K, so they may have some torsion, but I don't care about it. And the second, the global sections is a simple A module. The are simple pairwise non-isomorphic A modules, which are automatically finite dimensional because they're supported on this compact Y. A module. So then the statement is that the cycles, the support cycles of the corresponding things are linearly independent. So these are sitting in the, well, in the cohomology with support, whatever it is. In the homology with support, so it's actually in homology of dimension 2n of Y. Okay. So now this theorem, this second theorem, has an application, which was actually the question by Bezrukavnikov and Losev, to conical symplectic resolutions. So this second theorem, which was our which motivated our project. So applications. All right. So I remind you, since this is only interesting for people who have something to do with symplectic resolution, I will not give complete definitions. So I remind you that at least I just very quickly give a definition. So X is said to be conical symplectic resolution. If
Why is it the H2N?
because it's homologies, you think of it as a real manifold, right? All right. So it's said to be a conical symplectic resolution if first the affinization morphism. So you take the spec of the algebra of world affections, which is an affine variety. Which I'll denote by pi from X to X sub affine, which is by definition spec of the algebra of functions on X, is birational and proper. And second, this is the definition of what is a conical symplectic resolution. So yeah, and X is symplectic as from the beginning, from throughout. That's it. So this is one condition, it's just a condition. And the second one is a data. So X is equivalent to the C star action. Such that, first of all, the symplectic form has a strictly positive weight. The symplectic form of X. Two forms. And second, so our C star action induces an action on every object associated to X, in particular on X, the affinization of X. And the required condition is that the C star action contracts X now to a single point, which is a fixed point. A point which is traditionally denoted by 0. And there are lots of examples of these symplectic resolutions, equivarieties. I mean, they play now. They This is what geometric representation theory is doing. All right. So now in this setting, the notion of deformation quantization can be replaced by a slightly different notion of filtered quantization, I believe due to Ivan Losif. At least this is the only reference I know. And this has an advantage that there is no formal Planck constant h bar, and one just has filtered algebras instead of these algebras over formal power series. So I will not tell much about it. So then one can consider filter quantizations. I'll denote it by A sub x. So it's a sheaf of filtered algebras of OX, such that the associated graded is my OX. This is now filtered, and so one can take, it makes sense to take an associated graded. And then the global sections is a filtered algebra. And one can show that the associated graded algebra is what you would expect. Do I need any notation for it? Is global sections of x OX, which is also the same as the coordinate ring of x. Essentially, the two constructions, the formal deformation quantization and this filtered quantization, are related like Riesz algebra construction. So it's really very simple. And then another thing is that, maybe I should write it here, is that in this situation, the variety y is the zero fiber of my affinization map. So I will take y to be phi inverse of 0. And this is a projective variety because my morphism is projective. So yes, projective. But typically it's extremely singular. For instance, an example would be of a symplectic resolution is the Springer resolution, and this is then Springer fibers. So all right, and then again, if I start with a sheaf, a quantum sheaf with supported on y, then the global sections are finite dimensional, as I explained before. And then, since we're in the filtered setting and we have this property, it makes sense to consider, singular support, which is the support of the associated graded, as usual, with respect to the good filtration. And then if you translate my theorem 2 into this setting, you get the following statement. Corollary. I'll be a little bit sloppy, but let again sub alpha be a collection of OX for this case, probably I don't need. So let me give some other notation for this. Let's call them M sub alpha is a collection of all of this A sub x modules such that the support of this m sub alpha of the associated gradient of m alpha is contained in Y. Second, all non-zero cohomology vanish. And third, the global section, the zero cohomology are simple and pairwise non-isomorphic. Simple pairwise non-isomorphic. A modules. Then the statement is that the the characteristic cycles of the M alpha are linearly independent.
So this will be finite dimensional A module?
Yes, I mean, it's supported on Y. So it's automatically finite dimensional. Then I will. That's the proof. So it's a very elaborate version of what you did with Travis Shatter, and I will mention this.
But characters of non-isomorphic finite dimensional.
No, but the point is to relate characters to characteristic cycles. That's the main point. Yeah. Character. In particular, the number of such simple modules is bounded above by the number of irreducible components of the zero fiber. The central fiber. Well, the central fiber may have components of smaller dimension than the Conforget program. So it's even better. But typically it's Lagrangian, so you actually get all components of such simple modules. Is less than or equal to the number of irreducible components of Y. And I didn't say that Y is automatically of dimension at most n, but may have components of dimension less than n.
Does this last statement, does it follow from our theory with Schrader?
No, not at all, because no, it's your theorem follows from this, but not. No, I mean, you didn't do anything about characteristic cycles.
No, but irreducible components of Y correspond to the homology, the top, like middle homology of X, right? Or,
okay, let's discuss it after. I don't think it follows, but we can discuss it. Yeah, so basically, in the case where X is equivariety, that was the original question of Bezrukavnikov and Lossev. In that case, they managed, in the situation they were interested in, they managed to prove it in some very complicated way. And the question was whether it has a more general flavor. So this is what our motivation is. So now let's discuss the proofs. I'm not sure how much time. When did it start?
4:12.
4:12. Okay. So I will try to. So the proof, I mean, we first tried to prove for a very long time using some kind of naive geometric methods, and we completely failed. And so the proofs are involve some very strange thing, which is called cyclic homology. Which looks kind of weird in this setting, but now I will just basically introduce notation. So for any, it's some very general stuff. So for any DG category C, one can associate various homological objects. Namely, I will be interested in Hochschild homology of C, in periodic cyclic homology. So this is Hochschild homology. This is pH, periodic cyclic homology. And also negative cyclic homology. Experts in this stuff know that there's no, you see that there's no notion of cyclic homology itself here, and people know that negative are more important than ordinary. So it's HC minus of my C. C. So this is negative cyclic homology. Okay, so now all we need to know about it is two things. So first of all, there are canonical maps from this, the most important one, which is HC minus. So first of all, it maps to the periodic cyclic, and also it maps to Hochschild. And the second thing is that there is a Chern character in this setting. So Chern character map. H from the Grothendieck group of my category. C to negative cyclic homology. And then using the other maps, you can map them to other stuff, but the most refined version is negative cyclic homology. Okay, and so now the categories that are relevant for me are the categories of modules over OX or over quantized algebra with support in Y. So I'm interested in the case. So I'll denote by, let's say, HC minus sub Y of OX or of H bar. So this is the upper thing for C for my category equal to coherent OH bar modules with support in Y, and also for OX itself. Okay, and now the main theorem, which I'm going to write down later, just in a second, basically the main point is the following. So quantization, so replacing OX by OH bar, has the following effect. It does not change periodic cyclic homology, which is well known for experts. Periodic cyclic homology is kind of depends flatly on the parameters, but it drastically shrinks negative cyclic homology, and this is key. So of HC minus, but shrinks. So sorry, it's HP, but shrinks HC minus by about half. So it kills about half degrees.
HT was formerly TH, right?
Did I say? So I switch. Sometimes I write pH and sometimes HP. I don't. It's the same thing. Yeah, they come in. Yes. All right. So now I will say it formally. So this will be a big diagram, and this is in a sense the main theorem. Which says more precisely what happens. So the main theorem. So we have the following diagram. So again, we extend scalars to formal Laurent series. And then we have the following. So we have a K tensor over C of double bracket H with periodic cyclic, okay, so whatever they are, of all of H bar. So when I write arrows, this means that there is an isomorphism, which we actually construct with the direct sum of K tensor, the usual de Rham cohomology with support of X. And this part is just a cyclic homology of a non-quantized, which is well known to be H, so K of pH of OX. So this part, this equality is well known. The point is that this holds. And now inside here, we have negative cyclic homology. And the claim that this is actually injective. And under this map, it goes isomorphically to the direct sum over i's from 1. So this direct sum is over i's from 0 to the dimension of x, which is n. And this sum is all over i's from 0 to n, which is half dimension of x. And this is the main point. Such that the Chern character, so suppose I have a sheaf F and I have quantization. So the Chern character of my quantized sheaf F goes into this, under this, first of all, to the classical Chern character of F, of the classical sheaf, with some corrections. So one correction is very familiar in other subjects. This is called the Hirzebruch genus of X. It's some sort of similar to the Todd class of X. And there's another term, exponential of C of OH bar. This C is the Lin-Fedosov-Bezrukov-Kalledin period map of the quantization. Or maybe some other name, Stansevich, whoever.
The dimension of y is n at most, right?
Sorry?
The dimension of y is n, right?
No, this is completely general for any y. It's completely general.
No, what is n?
And where is? Okay. Yes, y is n-dimensional. But again, for arbitrary y, you just have to change n by some codimension or whatever, some number, depending on the codimension of y. I don't want to.
If the top sum 2i goes up to what?
To the real dimension of the corresponding manifold. 2n. 2n is the complex dimension. So real dimension is 4n.
X, not y.
dimension, well, just whatever complex dimension is, you can multiply it by 2 and get the real dimension. Well, this is correct. Uh, 2i in the top formula goes to 4n. Yes, that's okay. And at the bottom goes to 2n. Also, my notation, the Chern character I corresponds to, it sits in cohomological degree 2i, because they're all even degrees. Okay, where, so I just write what I say, C of O H bar is the line class. This class parameterizes the quantization I'm talking about. So now I will definitely not say anything about the proof. Maybe what I will say is that in this quantization business, the approach is an algebraic approach by Bezer-Kaufman of Palladium based on formal geometry, and we definitely use it. So what we use is and the one point of Bezer-Kaufman of Palladium is that they do not use much more general. Sorry. So they do not use much more general case covered by Kontsevich of Poisson varieties. But for this theorem, we do need Kontsevich. So in order, well, I won't explain it. So Kontsevich's formality theorem and certain explicit properties of the map, Kontsevich map. All right. So now I can try to, I have 10 minutes. I will sketch the proofs of my first two theorems. The first proof is completely trivial using this, and the second one requires it's related to Cauchy's questions. So proof of the vanishing theorem. So this is proof of, which is theorem 1. Well, the point is that the rank homology with support only lives in what is written. Actually, the right-hand side sits in 1 degree because the cohomology of support sits in degrees bigger than codimension. But this says that the negative. Okay, so let me write down. Since dy is n, implies from this that k tensor with hc minus of y of oh bar is isomorphic under my isomorphism to k tensor with h2n sub y x. So it just sits in 1 degree. Well, and now we take m. I don't take m. And now by the second statement of the theorem, this quantum Chern character goes to this. And so the quantum Chern character, because it's an element of HC minus, has to sit in this degree. So of H bar is concentrated. Because just the right-hand side doesn't. there is, it says that it sits in degree, HC minus is a direct sum of these degrees. But simply among those degrees, the non-zero cohomology with support, there's only one, because they sit just the geometric part, the ramp cohomology with support only sits in degree bigger than.
Oh.
So there are two opposite things. Just by geometry, topology, we know that all degrees have to be bigger than n, and this theorem says that they have to be smaller. So there's only one degree in degree 2n. But then my classical Chern character is equal, times. So therefore, this sits in degree, in the same degree. Constant is same degree. But all these factors are something starting with 1. So they're invertible things starting with 1 in degree 0. And then there are terms, correction terms. So then a hat is 1 plus ... And similar, the exponential starts with 1. So again, has the form 1 plus ... And so if this sits in 1 degree, then this has to sit in the same degree. And we're done. Okay, so now maybe I have 3 minutes. I will sketch at least the main idea of the proof of the linear independence. It's very similar to the idea. Well, it's one idea is a lemma from the first year or undergraduate algebra plus something fancy which comes from this. So let me, so again, we're in the setting where we have some quantum, I don't know, this F sub H bar. And now there is a kind of abstract Riemann-Roch theorem. Which says the following. Suppose I have an element of my algebra, non-commutative algebra of global sections of my quantization. Then I want to compute the trace. And suppose that this is supported on Y. So it has compact support. So the dimensional, all the cohomology is finite dimensional. And this is compact. Then, as usual in Riemann-Roch stuff, I may be interested in the following sum: trace of A acting on HI of my X H bar. Okay. Now the abstract Riemann-Roch says that this can be expressed in terms of characteristic classes. And more, so basic, sorry? Yeah, you need to, sorry, tensor with K. It's doing everywhere. Right. Unfortunately, we cannot really, what we would like is to write an explicit formula for what should be the right-hand side. We don't know that, and the problem is it turns out to be something I was very surprised with. There is no notion of any of these cohomology theories with compact support. In fact, there's no de Rham cohomology with compact support, which is even more surprising. But what we need for this is we don't actually need any explicit formula. What it says is that this is an expression, so it only depends on the Chern character of this and A. is of the form something like the Chern character of while this F H bar and A, where this angle bracket is something. I don't care what it is, it's the bilinear expression. It would be nice to have a kind of Riemann-Roch explicit formula for this. So this replaces some kind of integral over something, but I don't know even how to formulate this. Okay. On the other hand, there is a lemma, as I said, from undergraduate algebra, which says the following, that lemma, so let M alpha be a collection of simple finite dimensional modules over any algebra. Finite dimensional. Simple finite dimensional pairwise non-isomorphic modules over an algebra A. And then the trace functions are linearly independent. So this is essentially Wedderburn theorem. I used to give it an algebra 1. Also, Pasha likes it very much. Okay, so now we can prove what we want. Now, in the situation, in the assumptions of the theorem we want to prove is that my sheaf f of h bar has only zero cohomology. So the alternating sum on the right, on the left, reduces to h naught. Right. So Riemann-Roch. Now, the right-hand side of Riemann-Roch depends only on the quantum Chern character of FH. Okay, so this so by the right-hand side depends only. I mean, it's dependence of did I say is my notation? Yes. So depends only on. So its dependence on F is only through its Chern character. This is F H bar. By our main theorem, the quantum Chern character is expressed in terms of the classical Chern character. So main theorem So depends only on the classical Chern character or the corresponding classical unquantized sheaf. But by the vanishing theorem, the Chern character sits in 1 degree, and its Poincare dual is the characteristic cycle. That's it. Yeah, and then we apply this elementary lemma. Okay, thank you.
So how difficult is this abstract Riemann-Roch theorem?
No, abstract Riemann-Roch theorem is abstract nonsense. So it's really nothing. The point would be to write a formula, but the problem is I don't know even how to make a statement. As I say, it should be a pairing between cohomology and cohomology with compact support. But it's not known, it's not clear. There's no definition of, let's say, Hochschild homology with compact support. I searched the literature, there's nothing. I mean, many people prove this, some kinds of abstract nonsense Riemann-Roch theory, it's always nonsense. So there is no interesting statement here.
Other questions?
There was a work by Sklarov in another setting. So it's
in the last part, when we are saying it depends only on the Chern character for F in general, why did we ignore the Deligne-Fedorov map?
sorry, say again. I don't.
It also depends on the Deligne-Fedorov map, right? Jordan, the period map of Deligne and Fedorov, which is
which
dependent
cell?
on the quantization.
So the quantization is fixed. So there are 3 terms. There's a Chern character. Well, I mean, in the quantum setting, it's just this.
Yes.
This is what is in the Riemann-Roch theory.
Yeah. Next step.
In the next step, I mean, because this is the product of this guy plus a hat, which is just an invariant of the manifold.
A hat is fine. The Deligne-Fedorov map is dependent.
I'm not sure.
Like exponential of C.
But the quantization is also fixed. So the C is fixed for all.
Okay. Thanks.
The only term that depends on the sheaf is this. And then we have collections. We want to prove that something is linearly independent for different things, for different Fs.
Yeah, I just had a clarifying question about theorem 1. So is it literally like that? And I mean, and there with no assumptions on the quantization? I think
No, I mean, a nice exercise is to assume that Y is actually smooth.
no, that's not what I'm. Suppose Y is smooth, but I mean, when we change the quantization, for example, we can twist it by like a line.
It
bundle.
cancels out. There's some cancellation going on.
No, but okay. So consider like a silly example where you quantizing cotangent bundle.
Yeah. Yeah.
Is a 0 section.
Yeah.
Then this is just local systems.
Uh-huh.
But then O is a quantizes for two.
Yes, but it's
and
not.
like,
One has to make.
Line bundle with quantized.
Yeah. So this is what I'm saying. So one has to be. It's the Chern character is not a cohomology class of Y. It's a cohomology class of X with support on Y. And so if you do this push forward, there's a correction which cancels out.
So this sort of Chern character for all line bundles will be the same.
Whenever they have quantization. I mean, there's also a condition to have a quantization, and then this condition is precisely cancels all that you want to cancel. I can show it in our paper. I can show the place where this calculation is done. It's very nicely cancels out.
No, but and also in this on this board, so you said that under quantization, the periodic cyclic homology doesn't change.
Yes, I mean, I had this big diagram. I think I have erased it.
Okay, so this follows from it.
This has it's well known. It's called the Gauss mining
Ah,
connection.
I
So
see.
this is not something surprising. The surprising thing is that the negative really drastically shrinks, which is something. I mean, there's no Gauss mining connection on the negative cyclic homology, and the point is that quantization kills half of it.
Okay, thanks.
Different.
Quantization. Once you quantize it, it drops. So it's not continuous.
So another question, if the finite dimensional part is not assumed, can we make a statement for A infinity modules?
Well, I mean, we need a finite dimensionality to look at the character. Otherwise, I don't know, to have the trace. So at least in the Riemann-Roch, we have to assume that we deal with finite dimensional spaces.
Thanks.
So maybe the statement itself holds of my previous theorem holds in more generality, that I don't know.
All right. Well, I think we better wrap it up here. Let's thank the speaker again. Now, please don't go anywhere because you'll get instructions about the group photo.
Not clear. Are we going to have our photos with masks on or?
Yes, sir. Yes, sir.
Mask off?
All right, so we're going to head to, in some kind of loosely organized group, we'll head to cross campus in front of the Sterling Memorial Library, and that's where we'll have the photo. But if you just mill around, someone will lead us. What's that? Oh, it's a turn off. No, they're gonna have to either we're gonna have to lead them or they have to find it on their phone.
I'm happy to lead them, but
Yeah, well, that's what we should probably do. Yeah, I'll switch all this stuff off here.